The Curious Cosmos Presence. Cosmic Life Cycles, The Birth and Death of Stars documentary film. Welcome, space enthusiasts. Have you ever wondered about the incredible journey that stars embark on from their fiery birth to their spectacular death? Today we're diving deep into the mesmerizing life cycles of stars, revealing the secrets of these cosmic powerhouses that light up our universe. In this video, you'll uncover the fascinating processes behind the formation of stars, witness their glorious main sequence lives, and explore the dramatic events that mark their ultimate demise. Whether it's the birth of a protostar or the explosive end of a supernova, every stage is a testament to the awe-inspiring nature of our cosmos. We'll start with the birth of stars, emerging from vast clouds of gas and dust called nebulae. You'll see how these celestial nurseries give rise to protostars, setting the stage for nuclear fusion to ignite. From there, we'll journey through the diverse types of stars, each with their own unique path determined by their mass and composition. As we delve into the life of stars, you'll learn about the main sequence phase, where stars spend the majority of their lives fusing hydrogen into helium. Discover how stars like our Sun, as well as massive blue giants, produce the energy that powers their radiant glow. Finally, we'll witness the dramatic death of stars. For medium and low-mass stars, this means a beautiful transformation into planetary nebulae and white dwarfs. But for high-mass stars, the end comes with a bang, literally. Supernova explosions give birth to neutron stars and black holes, reshaping the cosmos in their wake. By the end of this journey, you'll have a comprehensive understanding of the birth, life, and death of stars. This knowledge not only enriches our appreciation of the night sky, but also underscores the interconnectedness of the universe. So strap in and get ready to explore the cosmic life cycles of stars. Let's embark on this stellar adventure together. Chapter 1. The Birth of Stars. Our journey begins in the vast, dark regions of space known as nebulae, the stellar nurseries where stars are born. Nebulae are vast clouds of gas and dust, primarily composed of hydrogen and helium. These cosmic clouds are the raw materials for star formation. When regions within a nebula become dense enough, gravity takes over, pulling the gas and dust together to form clumps. As these clumps contract, they heat up, causing the nebula to glow. This glowing region is known as a protostar. One of the most famous star-forming regions is the Eagle Nebula, home to the iconic Pillars of Creation. Did you know? The Orion Nebula, visible to the naked eye, is one of the brightest nebulae in the night sky and a hotspot for star formation. Protostars and star formation. As the clump of gas and dust continues to contract, it forms a protostar. This early stage of star formation is characterized by intense heat and pressure at the core. When the temperature reaches about 10 million degrees Celsius, nuclear fusion begins. Fusion is the process where hydrogen atoms merge to form helium, releasing a tremendous amount of energy. This energy counteracts the gravitational collapse, stabilizing the protostar and allowing it to enter the main sequence phase of its life. During this phase, the protostar sheds its outer layers in powerful stellar winds, blowing away any remaining gas and dust. This marks the birth of a new star, ready to shine brightly in the cosmos. Fun fact: a protostar can take anywhere from a few 100,000 to a few million years to form, depending on its mass. The type of star that forms depends on the mass of the protostar. Stars come in various sizes and colors, each with unique characteristics. Red dwarfs. These small, cool stars have long lifespans lasting billions of years. Yellow dwarfs. Stars like our Sun fall into this category. They have moderate temperatures and lifespans of around 10 billion years. Blue giants. These massive hot stars are incredibly bright, but have short lifespans, often only a few million years. The mass of a star determines its fate, dictating how it will live and die. Larger stars burn through their fuel quickly, while smaller stars burn slowly, lasting much longer. Fascinating fact: blue giants can be up to 20 times more massive than the Sun and can shine tens of thousands of times more brightly. Now that we've explored the birth of stars, let's move on to their life stages in Chapter 2, The Life of Stars. We'll see how these stellar objects evolve and change over time, producing the energy that lights up our universe. Stay tuned. Chapter 2, The Life of Stars. Once a star is born, It begins a dynamic journey through various stages, each with its unique characteristics and phenomena. Let's explore the fascinating life cycle of stars, diving deep into the mysteries that keep scientists and astronomers gazing at the night sky in wonder. The main sequence is the longest and most stable period in a star's life. During this phase, stars fuse hydrogen into helium in their cores, producing the energy that makes them shine. This balance between gravitational collapse and outward pressure from nuclear fusion defines the main sequence stage. Yellow dwarfs. Our Sun is a typical yellow dwarf. It has been in the main sequence for about 4.6 billion years and will remain there for another 5 billion years. Imagine that. In cosmic terms, our Sun is still in the prime of its life. Red dwarfs. These smaller, cooler stars burn their fuel slowly, allowing them to live for tens to hundreds of billions of years. They are the most abundant stars in our galaxy, making up about 70 to 80% of all stars in the Milky Way. Despite their abundance, red dwarfs are difficult to observe with the naked eye due to their low luminosity. Blue giants. Massive and hot. Blue giants burn through their hydrogen quickly, lasting only a few million years before evolving into the next stages. Their immense energy output means they live fast and die young, leaving behind spectacular cosmic remnants. Did you know? Main sequence stars like our Sun convert about 600 million tons of hydrogen into helium every second. That's equivalent to converting the mass of about 100 Great Pyramids of Giza into energy every second. Life cycle stages. As stars exhaust their hydrogen fuel, they leave the main sequence and evolve into red giants or supergiants, depending on their mass. Red giants. When a medium-mass star like the Sun runs out of hydrogen, its core contracts, and the outer layers expand, cooling and reddening in the process. The star becomes a red giant, with a diameter up to 100 times that of the Sun. During this phase, the star can produce elements such as carbon and nitrogen through helium fusion. Supergiants. Massive stars follow a similar path but become supergiants, expanding to even larger sizes. They continue to fuse heavier elements in their cores, creating layers like an onion. Supergiants are the cosmic forges where many of the elements essential for life are created. As these stars expand, the fusion process changes. Helium fusion starts producing carbon and oxygen. In supergiants, this fusion extends to even heavier elements like silicon and iron. The core temperatures of these stars can reach up to billions of degrees, enabling the formation of elements all the way up to iron on the periodic table. Fascinating fact. Red giants can engulf nearby planets, and when our Sun becomes a red giant, it may expand to engulf Mercury, Venus, and possibly Earth. Imagine the sight of our solar system's inner planets being consumed by an expanding Sun. Interesting insights. Some red giants become variable stars, pulsating in brightness as their outer layers expand and contract. These stars, known as mirror variables, can be seen flickering in the night sky. Many stars, including giants, are found in star clusters. Observing these clusters helps astronomers understand stellar evolution, as the stars within a cluster are typically the same age but vary in mass. High-mass stars and stellar evolution. The process of a star's evolution depends on its mass. The most massive stars undergo the most dramatic changes, leading to spectacular ends. These high-mass stars evolve quickly and dramatically, going through stages like blue supergiants and yellow hypergiants before meeting their ultimate fate. In the core of these stars, the fusion of heavier elements continues until iron is formed. Iron cannot fuse into heavier elements without consuming energy, leading to a critical point in the star's life cycle. Now that we've explored the life stages of stars, from their stable main sequence phase to their dramatic expansions into giants and supergiants, we prepare to witness the most awe-inspiring and sometimes violent events that mark the end of a star's life. Stay tuned as we dive into Chapter 3, The Death of Stars, where we'll witness the powerful forces that reshape the cosmos and give birth to new celestial phenomena. Chapter 3, The Death of Stars. While the life of a star is marked by stability and transformation, its death is a dramatic and often violent event that reshapes the cosmos. Join us as we explore the spectacular ends of stars, from the gentle fading of white dwarfs to the explosive power of supernova and the mysterious formation of black holes. When stars like our Sun exhaust their nuclear fuel, they don't explode, but instead undergo a series of changes leading to a more peaceful end. As a medium or low-mass star becomes a red giant, it sheds its outer layers, creating a stunning planetary nebula. These nebulae, often spherical or ring-shaped, glow brightly as the exposed core of the star heats the ejected gas. The remaining core of the star becomes a white dwarf, a small, dense remnant roughly the size of Earth, but with a mass comparable to the Sun. White dwarfs no longer undergo fusion. Instead, they gradually cool and fade over billions of years. Interesting fact, a single teaspoon of white dwarf material would weigh as much as an elephant on Earth. This incredible density is due to the collapse of the star's core under gravity. High-mass stars have a much more dramatic end, leading to some of the most powerful and awe-inspiring events in the universe. When a high-mass star's core collapses, it triggers a supernova explosion, one of the most energetic events in the universe. This explosion can outshine entire galaxies for a brief period, dispersing elements forged in the star's core into space. Supernovae plays a crucial role in seeding the universe with heavy elements like iron, gold, and uranium, which are essential for planet formation and life as we know it. Fun fact: the Crab Nebula, a remnant of a supernova observed in 1054 AD, still expands at 1,500 kilometers per second. Imagine the immense energy required to propel matter at such speeds. Formation of neutron stars and black holes. Neutron stars. If the core's remaining mass is between 1.4 and 3 times the mass of the Sun, it becomes a neutron star. These incredibly dense objects are only about 20 kilometers in diameter, but contain more mass than the Sun. Neutron stars are made almost entirely of neutrons, and they can spin rapidly, emitting beams of radiation as pulsars. Black holes. If the core's mass exceeds about 3 times the Sun's mass, it collapses further to form a black hole. Black holes have such strong gravity that not even light can escape them. They warp space-time, creating phenomena like gravitational lensing and accretion disks around their event horizons. Fascinating insight. Neutron stars have magnetic fields trillions of times stronger than Earth's, and a single cubic centimeter of neutron star material would weigh about 1 billion tons. Impact on surrounding space. Stellar winds and gamma-ray bursts. The death of high-mass stars can also produce intense stellar winds and gamma-ray bursts, which can affect nearby star systems and even trigger the formation of new stars. Cosmic recycling. The elements dispersed by supernovae enrich the interstellar medium, contributing to the formation of new stars and planets. This cosmic recycling ensures that the materials essential for life are spread throughout the galaxy. The death of stars marks the end of one chapter and the beginning of another in the cosmic story. As we continue our journey, we will explore the remnants left behind by these stellar giants and their profound impact on the universe. Chapter 4. Stellar Remnants. After the spectacular deaths of stars, what remains are some of the most fascinating and mysterious objects in the universe. These remnants hold the secrets to understanding the life cycles of stars and the ongoing processes that shape our cosmos. Let's start with white dwarfs, the remnants of medium and low-mass stars. These dense, compact objects are formed when a star sheds its outer layers, leaving behind a core that no longer undergoes nuclear fusion. White dwarfs are incredibly dense. A single cubic centimeter of white dwarf material would weigh tons on Earth. These stars slowly cool and fade over billions of years, eventually becoming black dwarfs, although the universe is not old enough for any black dwarfs to exist yet. Fascinating fact. White dwarfs have surface gravities 100,000 times that of Earth. This means a human weighing 70 kilograms on Earth would weigh 7 million kilograms on the surface of a white dwarf. Next, we explore neutron stars, the remnants of massive stars that have undergone supernova explosions. Neutron stars are among the densest objects in the universe, with properties that boggle the mind. Interesting insight. Neutron stars can spin at incredible speeds, with some rotating hundreds of times per second. These rapidly spinning neutron stars are known as pulsars, emitting beams of radiation that sweep across space. Neutron stars are incredibly small, only about 20 kilometers in diameter, yet they contain more mass than the Sun. They are composed almost entirely of neutrons, packed so densely that a single teaspoon of neutron star material would weigh about 1 billion tons. Pulsars act as cosmic lighthouses, their beams of radiation detectable from Earth as regular pulses of light. Magnetars, a type of neutron star with extremely powerful magnetic fields, can produce bursts of X-rays and gamma rays that are detectable across the universe. Fun fact, the magnetic field of a magnetar is so strong that it could strip the information from your credit card from halfway across the moon. Black holes. Finally, we arrive at black holes, the most enigmatic and extreme of stellar remnants. Formed from the collapsed cores of the most massive stars, black holes have gravitational fields so intense that not even light can escape them. Black holes are defined by their event horizon, the boundary beyond which nothing can escape. The core collapses to an infinitely dense point called a singularity, where the laws of physics as we know them break down. Fascinating fact. The event horizon of a black hole is not a physical surface, but a point of no return. Anything that crosses this boundary is inexorably pulled towards the singularity. Effects on space-time and surrounding matter. Black holes warp the fabric of space-time, creating gravitational lensing effects that can bend light from distant stars and galaxies. Matter falling into a black hole forms an accretion disk, heating up and emitting intense radiation as it spirals inwards. Some black holes are believed to be at the centers of galaxies, including our own Milky Way, where they play a crucial role in the dynamics and evolution of galaxies. Chapter 5. The Cosmic Impact of Stellar Evolution. We've journeyed through the birth, life, and death of stars, but what about their impact on the cosmos? In this chapter, we'll explore how stellar evolution shapes galaxies, influences planetary systems, and even seeds the universe with the building blocks of life. Buckle up, because the ripple effects of stellar life cycles are more profound than you might imagine. Supernovae, the explosive deaths of massive stars, play a critical role in the evolution of galaxies. When these stars go supernova, they release vast amounts of energy and matter into space, triggering a series of cosmic events. Galactic recycling. Supernovae eject heavy elements into space, enriching the interstellar medium with materials like iron, gold, and uranium. These elements are essential for forming new stars, planets, and even life itself. Without supernova, the universe would lack the diversity of elements needed for complex chemistry. Each supernova explosion releases energy equivalent to the total output of the Sun over its entire lifetime in just a few seconds. The shock waves from supernova can compress nearby gas clouds, triggering the formation of new stars. This process of star formation and death drives the continuous cycle of stellar evolution, shaping the structure and dynamics of galaxies. Beyond supernovae, stellar winds from young massive stars also play a crucial role in shaping planetary systems. These powerful winds can sculpt and influence the formation of planets. Stellar winds also play a role in the habitability of planets. For example, a planet's magnetic field can protect its atmosphere from being stripped away by stellar winds, as seen with Earth and its protective magnetosphere. Stars are not just the forges of elements. They also seed the cosmos with the ingredients necessary for life. When stars die, they release stardust, tiny particles that carry complex organic molecules. In the cold depths of space, simple molecules can combine to form complex organic compounds, including amino acids and other building blocks of life. These molecules are found in interstellar dust clouds, comets, and even on the surfaces of planets and moons. Fascinating fact, the organic molecules found in space include amino acids, the building blocks of proteins, which are essential for life as we know it. Panspermia hypothesis. One intriguing idea is the panspermia hypothesis, which suggests that life on Earth might have been seeded by organic molecules delivered by comets and meteorites. This hypothesis implies that the building blocks of life could be widespread throughout the universe, increasing the chances of life existing elsewhere. As we conclude our exploration of the cosmic impact of stellar evolution, we are left with a profound appreciation for the interconnectedness of the universe. The life cycles of stars are not isolated events, but a part of a grand cosmic dance that shapes galaxies, forms planetary systems, and potentially seeds life itself. Chapter 6. The Future of Stellar Exploration. We've journeyed through the birth, life, and death of stars and examined their profound impact on the cosmos. It's time to look ahead. What does the future hold for our quest to understand the stars? From next-generation telescopes to ambitious space missions, let's explore the cutting-edge technologies and missions that will push the boundaries of our knowledge. and bring the universe closer to us than ever before. The future of stellar exploration is bright, with a new generation of telescopes set to revolutionize our understanding of the universe. These powerful instruments will provide unprecedented views of stars, galaxies, and cosmic phenomena. James Webb Space Telescope. Launched to replace the Hubble Space Telescope, the JWST is equipped with a larger mirror and advanced infrared capabilities. It will peer deeper into space and further back in time, revealing the formation of the first stars and galaxies. The JWST's primary mirror is over 6.5 meters in diameter, allowing it to collect more light and see fainter objects than ever before. Extremely Large Telescope, ELT. Set to be the world's largest optical, near-infrared telescope, the ELT will have a 39-meter mirror. Its incredible resolution will enable astronomers to study the atmospheres of exoplanets and the details of stellar evolution. 30-meter telescope, TMT. With its 30-meter mirror, the TMT will provide unprecedented clarity and detail, allowing for direct imaging of exoplanets and deep insights into star formation and the dynamics of galaxies. Beyond telescopes, a series of ambitious space missions are set to explore the universe in ways never before possible. These missions will extend our reach into the cosmos and uncover new insights about the stars. Nancy Grace Roman Space Telescope, named after NASA's first chief of astronomy. This telescope will have a wide field of view and is designed to study dark energy, exoplanets, and infrared astrophysics. LUVOIR, Large UV Optical IR Surveyor, a proposed space observatory with a massive segmented mirror. LUVOIR will study everything from the formation of galaxies to the atmospheres of exoplanets, potentially identifying signs of life. Starshot Initiative, an audacious plan to send tiny, light-propelled spacecraft to Alpha Centauri, our closest neighboring star system. These miniature probes could travel at a significant fraction of the speed of light, reaching Alpha Centauri in just a few decades. If successful, the Starshot Initiative would be humanity's first interstellar mission, providing close-up images and data from another star system. The future of stellar exploration is not just about hardware. Breakthroughs in astrophysics and technology are also key. Innovations in computational power, artificial intelligence, and quantum technology will enable new ways of analyzing and understanding the data we collect. AI algorithms are already helping to process vast amounts of astronomical data, identifying patterns and anomalies that humans might miss. Future AI advancements will further enhance our ability to discover new stars, exoplanets, and cosmic phenomena. Quantum computers, with their extraordinary processing capabilities, will revolutionize simulations of stellar processes, helping us understand complex phenomena like supernovae and black hole mergers. Quantum computing could simulate the entire life cycle of a star, from formation to death, in unprecedented detail, providing new insights into the processes that drive stellar evolution. As we look to the future of stellar exploration, we stand on the brink of a new era of discovery. The technologies and missions we've explored in this chapter are just the beginning. The universe holds countless secrets, and with these advancements, we are poised to uncover them. Reflecting on our cosmic journey, we've traveled through the cosmos, witnessing the incredible birth, life, and death of stars. We've explored the cutting-edge technologies and ambitious missions that will shape the future of stellar exploration. Now let's reflect on what we've learned and what it means for our understanding of the universe. From the majestic birth of stars in nebulae to the awe-inspiring supernovae that signal their deaths, our exploration has revealed the dynamic and interconnected nature of the cosmos. We've seen how stars are not just isolated entities, but are integral to the fabric of the universe, influencing the formation of planets, the creation of elements, and even the potential for life. Key points recap. The birth of stars. Nebulae and protostars come together through the force of gravity, igniting nuclear fusion and giving rise to new stars. The life of stars. Main sequence stars fueled by hydrogen fusion shine for millions to billions of years, shaping the universe around them. The death of stars. Depending on their mass, stars end their lives as white dwarfs, neutron stars, or black holes, each leaving a unique legacy. Stellar remnants. White dwarfs cool over time. Neutron stars pulse with incredible energy, and black holes warp space-time itself. Fascinating fact. Did you know that every atom in our bodies was forged in the heart of a star? We are truly made of star stuff. Stellar exploration has far-reaching impacts beyond just scientific knowledge. It fuels our curiosity, drives technological advancements, and inspires future generations to look up and dream big. The pursuit of understanding stars pushes the boundaries of what's possible and challenges us to think beyond our own world. Key contributions: technological innovations, developments in telescopes, space travel, and computational power. Educational inspiration, encouraging the next generation of scientists, engineers, and explorers. Philosophical insights, helping us grasp our place in the universe and fostering a sense of wonder and humility. Space exploration has led to everyday technologies like GPS, medical imaging, and even the improvement of solar panels, showcasing the practical benefits of studying the stars. As we conclude our journey, we look to the future with excitement and anticipation. The next era of stellar exploration promises to unveil even more mysteries and wonders. With advancements in technology and a growing global interest in space, the possibilities are endless. The universe is expanding at an accelerating rate, driven by a mysterious force known as dark energy. Understanding this phenomenon could revolutionize our knowledge of cosmology. As we gaze up at the night sky, let's remember that every star tells a story of creation, evolution, and transformation. The stars are not just distant points of light, but are the very essence of the universe, shaping everything we know and everything we are. Thank you for joining us on this incredible journey through the life cycles of stars. The universe is vast and filled with endless possibilities, and our exploration is far from over. Keep looking up, stay curious, and let the wonders of the cosmos inspire you to reach for the stars. If you've enjoyed this journey and want to see more, don't forget to like, subscribe, and hit the notification bell. Together we'll continue to explore the mysteries of the universe and uncover the secrets of the stars. Thank you, and until next time, keep exploring the cosmos